Hi guys, in this video we'll continue looking at the chemistry of alkynes, and we will pick up here with section C, reduction of alkynes. And this will, the first two reactions here will be hydrogenation reactions where we use hydrogen gas. Now if you remember, we did hydrogenate an alkene and that led to the alkane. It's a syn addition of hydrogen to the pi bond. Well, likewise, we can hydrogenate the pi bonds of an alkyne. Hydrogen gas and a precious metal catalyst such as palladium, platinum, or nickel. Those are the three most common. And we know it is a syn addition, meaning the H's come from the same side, because they come from the metal surface, the catalyst surface. And thus, after we add two H's to the alkyne, we get an alkene. If you want to draw in the two H's, we can. And you see that they're going to be cis to each other. But when we say this molecule is cis, that refers to the substituents on the alkene, and that would be the methyl groups. But of course, if the H's are cis, then the methyl groups are going to be cis, and that's what is what the cis actually refers to. So that's just a simple addition of hydrogen. There's no regiochemistry here. There's an H on each carbon. It's not like we're adding HBr where we have to consider where does the H go and where does the Br go. And H is an H. But this is in brackets. And when we put something in brackets, that indicates that it's not isolated, and it will continue on, and a further reaction will take place. Now, in looking back, I don't know if I clarified that. Maybe I did, but when we hydrate an alkyne, we get an enol. And that was in brackets because the enol is not isolated, but it immediately undergoes a tautomerization to a carbonyl compound. And so that was in brackets. It continues on, and this is the final product. But this is an intermediate that we can show. It's a neutral intermediate. Now, of course, there's mechanistic intermediates. So, in brackets, we know that an alkene can be hydrogenated as well. We've already covered that reaction. Indeed, that occurs here. And when you add another equivalent of hydrogen across the pi bond, that gives you no pi bond, and now we have two H's on each carbon, and that is now a regular alkane. And so we can, if we wanted to just not show this intermediate, we could go directly here and say hydrogen and your favorite precious metal catalyst, maybe platinum, nickel, etc. But we could note that we would need two equivalents of hydrogen, 2 molar equivalents, and that takes it all the way to the alkane, where as presented it shows you sort of stepwise. One equivalent gives you the alkene, cis alkene, but that's not isolated. It continues on another equivalent all the way down to the alkane. And again, we call this hydrogenation, but it's also called a reduction because when you add H's, that's typically a reduction. Okay, pretty straightforward. It's just kind of twice the fun. 2 pi bonds, they each get hydrogenated. Well, question, what if you wanted to stop at the cis alkene? Can you? Well, not using a standard catalyst like platinum, nickel, or palladium, But if you use a poison catalyst, we can stop at the cis alkene. And a poison catalyst is where we add something to the catalyst that makes it less potent. And that can be done. You know, chemists tend to try lots of research, trying to develop some ingenuity, and things are developed. It turns out if you add some heavy metal salts such as barium salts or lead salts to palladium, it will sort of moderate the activity of the palladium. And we thus call, it makes it less potent, and we can kind of, in general, call this a poison. Now, it doesn't necessarily mean it's a poison to humans, it's a poison to the palladium. That's what the poison refers to. Now, at the same time, that doesn't mean it could also be a poison to humans. But we're poisoning the palladium here. Now, Lindlar's catalyst is actually a complex mixture of things. I'm not even going to show you what it is. You can look it up probably on Wikipedia. It is a palladium-based. I think it has perhaps lead added. It also has an organic amine added. Those are also known to be poison to the palladium. But anytime you see Lindlar's catalyst, that's a common example of a poison catalyst. And if you use a poison catalyst, it will stop at the cis alkene. But importantly, it will not continue on, okay? Not. That is, alkenes cannot be hydrogenated, are not hydrogenated if you use a poison catalyst. Thus, the reaction stops here. And so, think about it. We actually now have a synthesis, okay? You need to, I'm going to write this out here, but anytime we do a reaction, you need to think about, okay, what have we made? Here, we can convert an alkyne to an alkane, all right? Here we can convert an alkyne to a cis alkene, so it's a synthesis of a cis alkene. Okay. So two different hydrogenations, one with a regular catalyst all the way to the alkane. If we use a poison catalyst, it'll stop at the cis alkene. Well, next question. I'm sure some chemist, maybe 100 years ago, 150 years ago, asked, well, how can we convert an alkyne to a transalkene? And chemists went to work, and that has been developed. And that reaction is shown on the next page. If you take an alkyne and react it with sodium metal, okay? This is just oxidation state of 0. Sodium, there's no anion here. It's just neutral sodium metal. In ammonia as solvent, these reaction conditions, these reagents, will give a transalkene. Now, ammonia is a reagent typically. It's a fairly basic molecule. It's actually a gas, okay? Gas at room temperature. But if you cool it down to minus 33 degrees Celsius, it will be a liquid. Okay? And the liquid is under these conditions. And as a liquid, you can actually use it as a solvent to dissolve other things. Now, it's certainly not common, and you have to be careful about it. But it is used. So, the question here is, what is the mechanism for this reaction? We're not using hydrogen gas. There's no hydrogen gas, but we are adding two H's. We can draw those in just to clarify. Okay? We have added two H's to this molecule, but they do not come from hydrogen gas. Now, where do they come from? Obviously, they have to come from the ammonia, because there's nowhere else. They certainly don't come from the sodium. Now, the sodium is important. If an alkyne is not just going to react with ammonia. So what's going on here? Now, it is a reduction. We see that H's are added. That can tell us it's a reduction. Now, if you think back to Gen Chem, reduction typically meant, did we add electrons or remove electrons? Okay? Electrons added. So that's one meaning of reduction. Or H's added. And both of these are actually happening here. We've certainly added H's, but we've also added electrons. And we'll see that when we do the mechanism. And the electrons come from the sodium. Now, if you think about the chemistry of group 1 elements, they prefer to lose an electron to become like the previous noble gas. And if sodium loses an electron, it becomes like neon. And that's very favorable for sodium. Now, first step here. If you take sodium metal and put it in ammonia, liquid ammonia, you will generate what's called solvated electrons. How can we indicate an electron? A dot, or maybe an E minus? How about that? Because if we did an electron, a minus, that's a little bit, could become confusing. So, an electron. And the charge of an electron is minus. All right? And the sodium becomes sodium positive. It becomes like it would like to become. It loses an electron to take on the noble gas configuration of neon. And this electron is solvated by ammonia. Okay? You know, if we do hydrogen bonding, we take the H and we do an NCI to the lone pair. A lone pair of electrons. Well, this would be an NCI between the H and a single electron. And I'm going to do one NCI, but imagine this electron sort of surrounded by all these H's that are on ammonia. And we have a solvated electron. Now, this is quite interesting, peculiar, etc. Yes, you can look this up and read more about it. Now, this also is blue. Okay? Nice blue color, like my pen. Or, I knew I was going to be talking about this, like my shirt, or maybe a touch darker. That's pretty good, okay? Or my mouse pad, all right? If you look up online, you can probably find this reaction and see the color. And I may actually also have a video posted on the YouTube page, on the lab, in the lab folder. Okay. Well, that electron, even though it's solvated, it tends to be reactive. And this electron particle here will actually pump into the pi system. All right. If we take this and move it in here, now fishhook arrow. If we have a lone pair, all right, and we're going to move it, okay, we'd use a regular arrow. Maybe if it attacks like H plus or something. But if we have a single electron, all right, now this may not attack H plus, so I'm not quite sure what to... Okay, let's do this. Let's say we have a chlorine radical. We'll do this. They both have single electrons. If we come and do move one, it's just a half hook arrow. Not a full head, but a half header. It's called a fish hook arrow. And the other one we can come in here, and one electron and one of these are teaming up to give an HCl, and the two electrons have been moved to team up with each other. So if you're moving two electrons, it's a full arrow, one electron, a half hook or a half arrow or fish hook arrow. Now this is the first time we have ever used a fish hook arrow, because it's the first time we've ever moved. Let's go ahead and draw a dot here. Okay, I think the dot does work. Single electron is being moved in here, and then these two electrons, the pi bond, two electrons, move over here. And so that's a regular arrow. And that is going to give, if this moves over to become a lone pair. Okay? But I actually need to put the lone pair here, because at this point, with the alkene, the groups can be cis or trans, but they are going to be trans, simply because trans is preferred here. All right? Now my arrow really isn't meant to denote the stereochemistry that results here. If you want to draw this under, if that makes you feel better, answers any question there, because sometimes sometimes you guys tend to think that things mean more than they do, and so I feel like I need to show it like this, but the original was fine too. Now, what is over here on this other carbon? Well, a single electron. Because a single electron came in here and it pushed the pi bond, one pi bond over, and so instead of having a 2-electron pi bond, it moved over to become a 2-electron lone pair. But this thing should be charged, because if a minus is added to a neutral, this should be minus. And what is minus? It's actually this carbon here, because it owns 1, 2, 3, 4, 5. It's only supposed to own 4. This carbon on the left is neutral, because it owns 1, 2, 3 plus that electron 4. It's supposed to own 4. Reaction of a minus with a neutral should give a single minus. And trans is preferred simply because the groups have more space. It had a choice. All right. I mean, we could have proposed the groups being cis, but this would have been higher in energy because the groups are cis to each other. And since it's higher in energy, it would have had a higher transition state. A higher energy transition state. And energy is not going to go uphill if it doesn't have to. It's going to take the lower energy pathway, and the lower energy pathway is going to lead to the lower energy intermediate. Usually, and indeed it does here. Okay, at this point, this is a reactive carbanion, and it takes an H from ammonia. So these electrons bond to the H, these electrons move here. This is just a standard acid-base reaction. And that's going to give, what's bonded to this carbon now? Well, an H. One electron there. But importantly, what did we form here? Nitrogen, H, H, and one lone pair, but now we have two, right? And now that nitrogen is minus, but this is all neutral. Now we need another electron, and another electron comes from a second sodium. And it moves in here. All right. And that leads to boom, boom, boom. Got the H there. Now we have two electrons here, and now that's a minus charge again, just like here was. Really, we just repeat the process at sort of almost. Certainly here, just like we did over here, a second equivalent of ammonia can serve as an acid again. These electrons take an H. And uniquely here, ammonia is typically a base, but in this reaction it's actually serving as an acid. And this is going to give product plus another sort of conjugate base of ammonia. So this is a radical reaction. A radical is where you have a single unpaired electron. We generated radicals, you could say, free electrons, solvated electrons, very peculiar, but then electrons start pumping in here. The alkyne, or the resulting alkene, is an anion. It takes an H from ammonia. Another electron pumps in, form another carbanion, and it takes an H from ammonia. Now let's balance this out. We actually formed, in addition to the trans alkene, we formed two NaNH2s. Now, If I said we formed sodium chloride, you would know that is sodium plus and Cl minus. If I say it's NaNH2, you know that is Na plus NH2 minus. If we're going to show charge, we need to show complete everything, okay? Right? Let's do it like this, because I don't want to say that's a reaction. That is this. This is the same thing. Just like these two are the same thing. And didn't we form these? Where did we form them at? Right here? But we had to do this twice. First time gave us 1 electron, but we needed to do it again. So we actually had 2 of these. Okay? If we want to balance this out, 2 of those, 2 of these, 2 of these. And you actually need 2 ammonias, because we're using ammonia here and ammonia here. But we formed 2 sodium pluses, right? 2 of these. 2 of those, that means we have 2 of these and 2 of these. 2 sodium pluses and 2 of these. By the way, this is called sodium amide. And we formed one right there, and we formed the other one right here. So when I say we also formed 2 equivalents of the sodium amide, you see that we indeed did that. Now you got to be careful when we say amide. It's an NH3 is an amine. All right, NH2 minus is, well, what do you call an anion? Cl2 is chlorine. Cl minus is chloride. The ide ending. Instead of the amine ending, an ide ending gives us an amide. So sodium amide. Problem is, you know an amide is a functional group with a carbonyl, right? You don't need to write every single thing down here. That is an amide, but that is also an amide. All right? Unfortunately, both are called amides or amides. So again, sodium amide. Okay. There's some details here. There's also some terminology here. But the other thing is, you guys tend to have trouble recognizing, well, how did we form sodium amide? And why is it 2? Well, hopefully it's clear. We needed 2 electrons, and thus each sodium gives up an electron, so we're going to have 2 sodium pluses. And that's what this means. That's 2 sodium pluses. And then right here and right here, we form 2 of the amides. Okay. Let's move to the last topic in this handout here. D, acidity of terminal alkynes. We actually saw this when we looked at acidity during test 1. The H here on a terminal alkyne that's bonded to an sp carbon is slightly acidic with a pK of about 25. And we can remove it if we have a strong enough base. And the base that's very common is N-butyl lithium. Now this is a actual just alkane butane anion, and then the lithium plus. But this carbanion will take the H, leave the electrons behind, and form another carbanion. But this carbanion is more stable because the lone pair is an sp, where over here the lone pair is in an sp3 orbital. And so we're going to a more stable carbanion. And of course, when this takes an H, we would form butane. Now we can also see that this reaction is going to be favored if we look at the pKa's. 25, well, butane is much less acidic, pK of greater than 40. Which side's favored? Side with the weaker acid. This is favored by at least 10 to the 15. That is pretty much complete. N-butyl lithium is strong enough to remove the H from a terminal alkyne. Of course, the lithium would then sit with the anion here. This anion is often called an acetylide anion, ide ending. Although acetylene is just a 2-carbon alkyne, okay? I mean, that's acetylene, common name for that. If you make the anion here, it would certainly be the acetylide anion. But it's common to call almost any alkyne anion like this an acetylide anion. Now, a more general name is an alkynide anion. But you just don't hear that term quite as much. Okay, another base we can use to deprotonate terminal alkynes is actually the thing we formed up here, sodium amide. Because when we see this, we know we have NH2 minus. All right, but this can act as a base. Take that H, leave electrons behind, give that, sodium sits with that, and we form ammonia. So this is an acid-base reaction. And ammonia has a pK of about 35. And which side's favored? Well, the right. It's favored by 10 to the 10, and that's also enough to be fully complete. So these two bases will deprotonate terminal alkynes. What about something more common like sodium hydroxide? Well, we can certainly show that. These electrons take the H, stay behind. That would theoretically give the acetylide anion plus water. Well, the pK of water is 16. Which side's favored, 25 or 16? Well, actually, the left is favored. And so that means it's not going to come to the right, and so it's not going to happen. That is, sodium hydroxide is not strong enough of a base to generate or form the acetylide anion. And actually the reverse is favored. That is, if you have an acetylide anion and you treat it with water, it's going to go the other way, and these electrons will take the H and go back the other way. All right. We thus take from that is the acetylide anion is not stable in water. You cannot put it in water and expect it to survive. Now, understanding the reverse here, reaction of one of these with water, helps explain a common historical reaction, calcium carbide, which is actually a natural product. It's actually unique, CaC2. The C2 is actually a double acetylide anion. And then you have to have 2 pluses to counter balance that, and you have a calcium 2 plus sitting with that. It's actually, I don't think it's not actually a natural product, but it's formed from natural products, and it has been formed for many years before chemistry was even known, just by heating certain natural products. But if you take this, what happens if you put one of these acetylide anions with water? Well, we just showed that. All right. It will take the H, but it'll do it twice. You can do it on the other side as well. And what's that going to give? Put an H on each end, plus hydroxides. All right. 2 hydroxides, and the calcium will sit with the 2 hydroxides. But we made acetylene. All right, remember I told you acetylene? And this is a gas. All right, this over here is a solid. But acetylene gas is used to generate a flame. Either a flame for like a flashlight type of flame, or in a torch. Okay, you can look that up. But actually, used to be used in lanterns, and before batteries were developed, you could take calcium carbide and put it into this lantern, and then have a compartment where water was, and it would slowly drip on the calcium carbide, and the reaction would take place, and the gas would be slowly generated, and you could have it come out this little port here, and you could actually light it and have a continuous flame. And so this was one of the original sort of lanterns that you could light. And there's actually a video on the YouTube page that shows how this works. Now today, of course, these aren't used anymore. They're really just historical artifacts. But there was chemistry going on in this little container to generate this gas that could be lit. Again, understanding it's just a reverse of what we showed up here, because the pKa here is going to tell us that this will react with water to put the H back on. Okay, we're not going to go any further here. We're just going to form these anions, these acetylide anions. Now during test 3, we'll actually revisit this, and we'll use these anions for substitution reactions. And when we get there, I'll say, do you remember how we generated these? All right. Because deprotonation of the terminal alkyne, as shown above, will be the first step when we get to that chemistry later. All right. So there's some things to consider here. All right. Radical reaction, acid-base chemistry, revisiting the equilibrium, etc., and an application of that forming acetylene gas. Okay, guys, the remainder of this handout is some miscellaneous things. Hydration, okay, tautomerization. There's your mechanism on, resonance off. Remember the Oreo mnemonic? Okay. I reckon one thing I'll show you to end here is this very last page shows an example of an alkyne being hydrogenated to the alkane. All right. Now this is not a poison catalyst, so it goes all the way to the alkane to give this target compound here. Now, two fragments here were joined largely because of some chemistry that you can do with an alkyne, help put the molecule together, but then we can reduce it and go down to the more simple alkane structure that is wanted here. Okay guys, that finishes up the alkyne handout. I think we had 2 videos for that, and we'll see what type of questions come up.